Hello everybody, my name is Ethan Wanless, and this is my AstroBites presentation for stellar astrophysics. I've titled it, Any Way the Wind Blows, Circumstellar Matter Interactions with Type 1a Supernova Ejecta. The paper that this presentation is based off of is originally titled The Effect of Aspherical Stellar Wind of Giant Stars on the Symbiotic Channel of Type 1a Supernovae. This paper was originally published on February 19th, 2021, Beijing time, and the authors are, and I apologize if I mispronounce any of these names, Shengyuan Wu and Xiaofeng Wang of the Physics Department and Tsinghua Center for Astrophysics at Tsinghua University in Beijing, China, as well as Dongdong Liu and Bo Wang of the Yunnan Observatories in Kunming, China, and the University of Chinese Academy of Sciences in Beijing. Alright, so, first off, some important background information before we dive into the meat and potatoes of this paper. Some basic definitions here. Stellar wind is the stream of charged particles ejected from a star's upper atmosphere, and the exact composition and velocity, density, and properties in general of the wind vary based on the star's type and life stage. A giant star is a star that has stopped fusing hydrogen and left the main sequence. When this happens, the star begins fusing helium, which causes it to swell up to many times its original size and become dimmer and redder. Giant stars, this is important for the paper, giant stars have stellar winds with increased mass output but slower speeds compared to main sequence stars. A white dwarf, moving on, is a stellar remnant. It's the core of a low to medium mass star after all fuel has been exhausted. Or I guess more accurately, after all fusion has ceased. So without fusion to fight against gravitational collapse, the primary force preventing that collapse is electron degeneracy pressure. That last part doesn't have much to do with this paper, but it's very interesting, and I suggest you look it up on your own time. Finally, everyone's favorite, the supernova, an energetic and luminous stellar explosion. Now, normally, this is caused by the core collapse of a high-mass star in its final evolutionary stage, but there is one major exception, and that is Type 1a supernovas. These involve a binary system with a white dwarf and a companion star. And the companion here could be anything from a red supergiant to another white dwarf. And in this case, when I say could, I mean we don't really know exactly what type of binary system is the best progenitor of a Type 1a supernova. So this paper focuses on This paper focuses on one possible progenitor of Type 1a supernovas, which is systems with a giant star as the companion, and these systems are known as symbiotic binaries. So if we just focus on the bottom of the image I have on the right, this is how a Type 1a supernova is believed to kick off in the case of these systems. The aging companion star swells to a giant, and at this point, as you remember from the last slide, the solar wind's density and mass output increases. So this gives the white dwarf much more mass pushed in its direction to siphon off, much more matter, and it begins swelling and gaining mass. The white dwarf begins gaining mass, and eventually this mass reaches a critical point known as the Chandrasekhar limit. This is about 1.4 solar masses, and this is the maximum mass at which a white dwarf can be stable. Going past this mass leads to further core collapse and usually results in a Type 1a supernova. And the white dwarf is either collapsed further into a neutron star or sometimes even a black hole, but often it's destroyed completely and ejected as part of the supernova. Alright, finally some other terms that come up in the paper. Just abbreviations here. SN, supernova. SNE 1a, that's Type 1a supernova or Type 1a supernovae. CSM is circumstellar medium. Ejecta is the matter ejected in supernova explosions. WD is white dwarf. FGB is first giant branch, which is just an alternate name for red giant branch, and they use both RGB and FGB interchangeably in this paper. AGB is the asymptotic giant branch. TP-AGB is the thermally pulsing AGB. And MCH, that's the Chandrasekhar mass. So the purpose of this paper is, as I mentioned before, there's still no consensus among astronomers as to which binary systems are capable of being progenitors of Type 1a supernovas. So this paper aims to shed some light on that question. The researchers posit that the process of wind accretion by the white dwarf, when it's sucking up that solar wind and increasing its mass, likely produces large amounts of circumstellar medium, which is just the matter floating around the stars, hence the name, circumstellar medium. Examining the interactions between the supernova's ejecta and the CSM can, they're hoping, provide clues as to the composition, type, and exact life stage of the white dwarf's companion star, which will give us a better idea of what exact systems are the best progenitors for these supernovas. So the paper tests a method devised by the authors for estimating the density and geometric structure of the CSM, and then at the end briefly compares calculations that they made with real universe observations. So now we're getting into the meat and potatoes of the presentation. Before we begin, basis for calculation. So this is what the researchers have based their calculations off of, obviously. Their primary basis is the Stellar Evolution Code MESA. And MESA is an acronym which stands for Modules for Experiments in Stellar Astrophysics. This is an open source code for calculating the evolution of stars, and they used it to calculate the evolutions of binary systems with white dwarfs and giant stars, either in the free giant branch or asymptotic giant branch. And then they simulated those in both metal-rich and metal-poor environments, so the metallicity of the star, basically. So there were an abundance of very important figures in this paper, so I have had to choose just the small handful that I think are the most crucial. Here we have figure 6, which shows regions of initial companion mass and orbital period which can produce type 1a supernovas when the mass of the white dwarf is between 1.05 solar masses and 1.1 solar masses. So the two graphs on the left represent metal-rich environments, and the two graphs on the right represent metal-poor environments. Now, it's a little hard to tell what shapes are what on this graph, and I apologize for that. The images would not... They tried to cram a lot onto one page, so it was really hard to blow up much bigger than this. But the open circles on these graphs denote the mass of the companion star doesn't provide enough mass to push the white dwarf over the Chandrasekhar limit and create a supernova. The filled shapes, triangles, circles, and squares, represent a case where it was successful and a supernova did occur. Triangles denote the supernova as occurring in the weak H-shell flash phase. Circles denote the stable hydrogen burning phase, and squares denote the optical thick wind phase. So those are the phases of the companion star. The red dots represent instances where the core of the companion star was a helium core, and blue dots represent when the core of the companion star was a carbon-oxygen core. Oh, apologize for that. And then the x-axis is representative of days, and the y-axis is representative of the mass of the donor star, so the mass of the companion star. Here's our next set of important figures. This is figure 8, and in the upper graph, panel A, this shows the wind velocities versus mass loss rates of type 1a supernova progenitors from the symbiotic systems in the solar metallicity, so metal-rich environments. Actually, both of these are metal-rich environments, but the bottom graph is comparison of the relationship between the half-opening angle and the mass loss rate. So the y-axis is different between the two graphs. I'm going to focus on the upper one because that's much easier to understand. You just have the mass loss rate of the companion star on the x and the velocity on the right. So you can see that sloping negative correlation, where as the velocity decreases, or as the mass loss rate decreases, the wind velocity also decreases. And then here we have the same result except for metal-poor environments. So you can see slightly different correlation, but overall not a massive difference, especially on the velocity versus mass loss graph. And here's the final set of important figures. So we have figure 12 here. Basically what we have here is just these are the three graphs that we've looked at before, the three with the same axes, if you notice from top to bottom. But all we've graphed here is the exact parameter space that is successful in producing type 1a supernovas. So you'll notice right off the bat that a lot more of the successful supernova explosions came from systems with a helium core rather than a carbon-oxygen core, which I found to be counterintuitive. It's also worth noting that the left column is using a linear function and the right column is using an exponential function, hence the slightly different results. So, in conclusion, the researchers have successfully identified a range of parameters of symbiotic binary systems for which type 1a supernovas can be generated and how these parameters differ between metal-rich and metal-poor environments. These calculations were also able to, as they state in their paper, successfully reproduce some properties of the stellar wind interaction with the white dwarfs, which has been, or with the supernovas rather, which has been observed in the real world, or the real universe. Okay, so what? Why does all of this matter? Well, it actually does connect to our studies on a very basic level. So yeah, there's a lot of intense theorization going on, a lot of it's really difficult to understand, but at the end of the day, these are simulations made to try to better understand observations that we've seen of light emitted from two colliding hot clouds of gas, which is basically just an emission spectrum. So, you see, it all comes full circle. It all comes right back to Physics 101. Okay, so we're excited. I have the paper, obviously. It's worth noting that the captions on all of the figures, with the exception of the bullet point here, were taken directly from the paper to match right along with the figures. And then the one thing that wasn't from the paper was the supernova infographic, which I got from NASA's Hubble site. Alright, and that is my presentation. I am happy to answer any questions that you may have. And thank you for listening.